So if you get your big paper out that I gave you last time, it's the one that says the map of how to know how to name all types. We're going to go through that. If you don't have one, there's some in the brown crate by the microwave. I told them we'd start, so hopefully they'll hear. They said they'd watch the rest online. So.
So a couple of us are wondering that
That's what's in the hood. That's the ammonia. It's in the hood. It's in a beaker. It has things on it. It says NH4OH.
If you turn the corner right on the left, there's like a little cubby hole for this giant container.
Okay, so we're going forward. We're going to do this map real quickly. If it wants to get going here. Okay, so first thing that you need to ask is the first metal, is the first element a metal? Remember that the metals take up most of the periodic table. It's in the P if you do that diagonal from boron to unoxidation, and this way are metals. So if the first is a metal, the answer is yes. Then you need to ask, is the metal in the first two columns or the slide? If it is, remember the first column is a +1, second column has a +2. The slide, boron, aluminum, gallium are +3, zinc's +2, silver +1. If that is a yes, then it's type 1. And we just name it, name what it's with, change the ending if it's an element to IDE. If it's polyatomic, we keep it. But we have to balance the charges. But we know the charges, so we can do that. Okay, so it has to add to equal 0. If the answer to that is no, then we have type 2, and that's the type we have to use with Roman numerals. If you don't have, there's a sheet that I gave you guys. Jaron? It's Jaron, right?
Yeah.
There's a sheet over by the microwave that you can go grab that has all this on it. Did you get that big sheet? Yeah, you got it. Okay. All right, so this one is in the D, the F, or the lower part of the P. These ones right here have lots of different charges, so we have to use a Roman numeral to tell the charge on the first element, which is a metal. Okay, we're still having to balance it so it has an overall charge of 0, but we have to have a Roman numeral when we're writing the name of it. If we go back to here, if the first element is not a metal, then is the first element hydrogen? If the answer to that is no, whoops, wrong way, sorry. The answer to that's no, then we've got type 3. We don't have to worry about charges. We worry about how many of each one we have. We use the mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay?
Sorry, you said it was ammonium hydroxide in the back that you add 6 milliliters, and that's just 3 drops.
It's not, yeah. Yep. Okay, if that answer to that question is the first element hydrogen, then we have an acid. And an acid, we have to break down and say, okay, does it start with hydro? If it starts with hydro, that means it's just 2 elements, hydrogen and one other. Anytime I have an acid, it's going to be hydrogen as the positive ion. It's just what metal is it with, or what non-metal is it with, or what polyatomic is it with. If I don't have a hydro, and again, on acids, we do have to balance the charges, but we're just adding hydrogens to balance the charges. If I don't have hydro in front of the name, then it is hydrogen with a polyatomic. Remember my little thing, ate Thanksgiving dinner and afterwards I got feeling sick. So if I have hydrogen with a polyatomic and the polyatomic's name ended in 8, then I would name it whatever ic an acid. But I still am going to use that hydrogen to balance out the polyatomic's charge. If the polyatomic ended in ite, remember OS, we're going to get in a fight in an acid situation. So we change it to OUS and we put acid. Now if we are given the name OUS acid, something OUS acid, then we go backwards and say, oh, it's hydrogen with, to change the OUS to ite, find out that polyatomic, but you're still balancing the charges to 0. Okay, I'll give you a few minutes. Make sure you get a chance to get all that down. Yes, sir?
That word under number on type 3.
The number present. So it tells you how many of each element is present.
Can you give us an example of the acid stuff?
So acid for the hydro would be like hydrochloric acid, HCl. For a polyatomic one that has an ick, it could be like sulfuric acid, which is H2SO4. For sulfurous acid, we do H2SO3. So you have less oxygen with the OUS. Okay? So this is just summarizing the last two chapters we've been working on, Chapter 3 and Chapter 4. Since we have a year-end test, we want to make sure we have the summaries kept. Now, a smart thing to do, since I have to confiscate your 3x5 cards, is every time you make a 3x5 card for a test, is to copy that. So you have it when you get to the end of the year, you have 12 copied that have the most important, what you thought was the most important for each chapter there, and you can make one card for the whole.
Use those on the test?
No, but you can use it to make one for the last test. So you don't have to go back and try and figure out what did you think you need for Chapter 1, Chapter 2, Chapter 3.
For the final test, can we have one of those, like,
Nope.
cards?
Nope, yes.
Bottom one,
Present. Present.
it'll be a 3-foot bike.
No. Nope. Okay, we got all this down? Still needing a few seconds. Still seeing a couple head bobs. You're too young to have your neck hurt.
I just see that. Like when I go out, I like see my head like all the way down.
Okay, here we go forward into the new stuff. So this is Chapter 5. Chapter 5, I wish they would have split into more chapters, but we'll just make it work. Has a lot of information in it. We're going to be talking about chemical reactions and everything that has to do with chemical reactions. So, the general feature of physical and chemical changes. We did the lab on chemical and physical changes already. Physical change just means I'm changing something that I can change back. In other words, after I do something, I still have the same stuff, it's just in a different shape. So if I had bread, homemade bread, and I cut it, it's still homemade bread, I just cut it into smaller pieces. If I have ice and it melts, it's still water, whether it's ice or it's water. Or if I heat it up and it becomes steam, it's still water. So physical change is just changing the physical state of something or make it in smaller pieces. You're not changing the actual composition. You're not changing what water is as H2O. You're not making it H3O. You're just changing how they're arranged. Okay? On the chemical side, chemical change is a chemical reaction. So here I have wood that would be a cellulose. If I then burn the wood in a campfire, I end up with ash, which is a totally new substance from what cellulose was. So I actually break the bonds that are in my reactant, and then they reform to make new products. I can't put that ash back into wood. Okay, there are some reactions that are reversible, but for the most part, they don't go backwards.
What's one that can't get backwards?
The ammonium reaction, where you make ammonium. So if I take ammonium and water, I can make ammonium hydroxide, or if I leave ammonium hydroxide out, it makes ammonia and water. So that's what we used to develop our chromatography, was the ammonia coming off ammonium hydroxide. We okay to go forward? Okay, so writing chemical equations, we need to be able to know what is where. So reactants are always on the left, products are on the right, the arrow always points to the products. Coefficients are telling me how many of each thing I need. So coefficients are the bigger number in front of a compound. That tells me how many of each of those I need.
So like you need 1 CH4 plus 2 O2.
Yeah, so like when you're making a sandwich, I need 2 pieces of bread, I need a teaspoon of jam, and I need a teaspoon of peanut butter. Or tablespoon, depends on how much peanut butter and jam you like. Okay, but there's a ratio to put it together. Or if I'm making a cookie recipe, you know, I have 4 eggs, I have I have a specific amount of each thing to make these one cookies.
Well, those are literally a reaction anyways.
Yeah, it is, yes.
Could this kind of be comparable to like the equation you write like a physics class for like vectors going one way,
This is not vectors. You got to think of it a little bit different.
but like is it similar?
Sort of. So you're still going to have an end vector or end product. Okay, so with chemical reactions, we actually work with what's called the law of conservation of mass. I can't create or destroy matter. I can rearrange it, but I can't create or destroy it. So coefficients, those big numbers in front of those things, were used to balance the equation or to conserve matter. A balancing equation has the same number of atoms of each kind of element on both sides.
Go back to the last slide.
Did you get it? You need to be here for a minute.
Yeah, I got it.
Okay. How are we doing on this slide? Can we go on?
Almost.
Almost.
Yeah, you can go on.
Never mind. I like that. Yeah, you can go on. No, never mind.
Well, one of my friends, someone asked him to do something. He's like, no thanks. It's like, what do you say to that?
Okay. All right, here we go forward. So I've taken the equation and given you a visual representation of that same equation. So here we have CH4. This is what O2 looks like. This is what CO2 looks like. And this is what water looks like. Sorry, I didn't put them in the right order there. So we know that this side is my reactants. We know that this side is my products. Okay, so when we do conservation of mass, we have to look at each individual element. So there's one carbon on the reactant side, and there's one carbon on the product side, which is good. If we look at now the hydrogens, those are the white ones, there's 4 hydrogen atoms on the left side. There are only 2 hydrogen atoms on the right side. And the only thing that has hydrogen atoms was water. So I need to have 4 hydrogen atoms on this side. In order to do that, I need to add another water. Okay, so now my hydrogens are taken care of. Now I look at the and by doing that second one, I need to put the 2 there. Okay, so that tells me I have 2 water molecules. Over here on the left, we have 2 oxygen atoms, and on the right, we now have 4 oxygen atoms. Those are the red ones. So I need more oxygen on the reactant side. So I need to make this be 4, and to do that, I need another set of oxygen, because oxygen's diatomic. Now that gives me 2 here. That means I'm going to have to change that and make a 2 in front of the oxygen. Okay, so this is how we balance equations. And the reason it's balanced is I have the same number of atoms on the reactant as I do on the product. Okay, they have to be the same. I can't create or destroy matter. They have to be the same. We okay to go forward?
Do people actually like that equation?
Yeah, we use it all the time. We're going to use it next week. Okay, I want you to pick 2 colors that you like. Out of all the colored pencils right there, just pick 2. Okay, I've got limited amounts here, so I'm going to use blue for my products. And I'm going to use red for my reactants. Okay, so you have a table there that says products and reactants. We found out really fast first period that it was really monotonous to rewrite it. So just color the squares that say product with your color that you want to use for product. Color the squares that say reactant with the colors that you want to use for reactant. And then we're just going to circle them in the other side. So I have got my reactants color here, and I'm just going to circle anything that the arrow is not pointing to. Anything the arrow is not pointing to. These are my reactants, anything on the left side of the arrow. Then I'm going to pick up my product color, which is blue, and anything that the arrow is pointing to, that is my product. So I'm going to circle it as my product. If you want to shade it, you can shade it. Mine didn't shade very well, so that's why I'm circling it. But you could shade them. Yes,
Can we stay a little after school, finish that?
that's fine. Actually, I won't be here more than about 10 minutes after. Okay. All right. So we've identified the reactants or products. You need to be able to do that. This is not the hard part. So if you didn't get one of those, they're right here as you logged in.
Oh,
Okay? All right, going on. Equations are said to be balanced when matter is conserved. So when we conserve matter, that means I have the same number of atoms on both sides. In other words, if I was a teeter-totter, it would be balanced, the exact same. They actually weigh the exact same. If I have a balanced equation, my reactants, I can add up the mass. Products, I add up the mass, and it will be exactly the same. Okay, so when we balance it, this is what I do. I usually get a scratch piece of paper, but I gave you enough room here to do these on these 4. So we're just going to write on here, and then I'll pass out some scratch for you. But underneath the arrow, I put the elements that are in that equation, leaving H and O to very end. And this is how you remember it. At the end of the year, Christmas, Santa comes, ho, ho, ho. H-O, very end. That's the last 2 that you always want to balance. So if you have other elements, it's just H, then O. So H second to last, oxygen always last. And the reason we do that is it'll make it easier to balance most equations. Yes?
So in the first equation, it was H2 plus O2. We had carbon atom in there.
Then it would be above that. Yeah, and we'll do that with this one. Okay?
And nitrogen go up.
Any others can go up above, but just leave hydrogen and oxygen to the very last. So just write H and O underneath the arrow. And then on this side, we say, how many hydrogens are on this side? Well, there's 2. How many hydrogens on this side? There's 2. How many oxygens on the reactant side? There's 2. How many oxygens on the product side? 1. That is not balanced. So now I have to go back and say, okay, it's not balanced, so the only way I can balance is to put a coefficient, which is 2, here. But that changes this, and it changes this. Now my hydrogens are out of balance. So now I come back and say, okay, on the reactant side, I can put a 2 in front of this. That will change that to 4. It is now balanced. So I've conserved mass. On the next one down, we do have carbon. So we're going to put carbon, hydrogen, and oxygen. On the left side, we have 1 carbon. On the right side, we have 1 carbon. On the left side, we have 4 hydrogens. On the right side, we have 2 hydrogens. So right there, I stop because they're not the same and say, okay, I need to put a 2 coefficient in front of that, so that makes that a 4. Going to oxygen. Here I have 2 on the reactant side, which is the left, and on the product side, I have oxygen in 2 places. So I write it like this. I have 2 oxygens in the CO2, and I have 2 oxygens in the water because the 2 times is through. So I've got a total of 4 oxygens. So I come back over to my reactant side and say, oh, I need a coefficient of 2 here because 2 times 2 is 4, and that gives me 4, and now it's balanced. Yes?
I have a question on the first one.
Yes?
Why isn't it just H2O2 instead of 2?
That would be peroxide. That's not water. So here I made water. If I wanted to make hydrogen peroxide, then I can do that.
Oh, okay, so
But hydrogen peroxide takes a lot of energy to make, so we'd have to have some kind of thing over the arrows.
I didn't see that we were actually going for water there.
Yep. Well, we make it balanced by adding twice as many hydrogens. Okay. All right, so over here we don't have hydrogen or oxygen, so we just put F and Cl. Does it matter what order? No, it does not matter what order. You can choose whatever order you want as long as all the elements are there. So iron 1, iron 1. Then we get to chlorine. We have 2 on the reactant side, 3 on the product side. What am I going to do?
3 chlorine side.
So I need to get it to a 6 because all I can do is multiply.
All right,
So I need 3 over here. That will make it 6. I need 2 over here, and that will make it 6, but that messed with my iron. So I put a 2 over here, and I'm balanced. Okay? So you've got to be careful. If you have already balanced something and you have to put a coefficient in front of it, you need to make sure you go back and change that because it's got to be balanced in all elements. So this one's a little bit more. This is propane, burning propane. Okay, so some of you are familiar with propane. Okay, CHO again. Most combustion reactions are CHO. We have 3 carbons on the reactant side, 1 carbon on the product side. What do I need to do? Multiply the CO2 by 3. Good. Now hydrogens, I have 8 on my reactant side. I have 2 in the water on my product side. What do I need to do? Multiply the water by 4. Good. Now oxygens, I have 2 on the reactant side. On the product side, I've got to be careful because oxygen's in 2 different places. So the first one is 4 times 1, which is 4, plus the second one, CO2, is 3 times 2, which is 6, giving me a total of 10. So this side over here, the reactant side, I need to times by 5, so that will make 10, and I'm balanced. Okay? So I had given you room on the ones that we just did, but on the ones on the next, let's see, I think there's one thing more before we do more of them. There's some symbols that we need to know the meanings for. An arrow means a reaction's taken place. A delta over the arrow means that I've added or subtracted heat. Okay, so I've changed the heat. An S means solid, an L means liquid, a G means gas, and an AQ means aqueous. That means I dissolve something in water. And most things that we do in lab have been dissolved in water. Okay? So I'm going to pass some of these out. I'm going to give you a few to work with. You get a mixed color group. And you want to just keep some extras in your
So does the triangle, it means
change in heat. Okay, we're going to use these. You can just use any scratch paper. I just went to the copy center and got these pieces, and that'll be fine because she didn't have any other scratch paper at the time. So this is what I do. I always have a piece of scratch paper when I'm balancing equations because they usually give you a sheet like this, and there's no room to do what I was showing you how to do. And that makes it the easiest way to balance it. So I'm going to bring up a sheet of paper. That's going to be my scratch paper. We'll just go forward here. Okay, this is my scratch paper, and I just put it right underneath that equation. So you do that with one of those pieces. Hello, welcome. Focus. Put one of those pieces right underneath this equation in your notes. So it doesn't matter which direction you do it. I like to do it long ways, but it's okay because you can move it along and use it over and over again. So the scratch paper can be used over and over again. If I use just a regular piece of paper, I fold it and keep folding it till I used it all up. So underneath the arrow, I put my CHO. Okay? Or whatever elements I need. All right, on the right-hand side, we have 6 carbons. Sorry, left-hand side, thank you. Reactant side. On the product side, we have 1 carbon. So we need 6. So I'm going to put a 6 here, change that to a 6. Hydrogens. On the reactant side, I have 6. On the product side, I have 2. What do I need to do? Put a 3. Good. Now I have 6. On the oxygens, on the reactant side, I have 2. On the product side, I've got to be careful because it's 2 different places. 3 plus 6 times 2 is 12, gives me a total of 15. Now, on the reactant side, you'll notice that I can only get evens, right? Because it's times by 2. Whatever number I put there is times by 2. So I could go back and I could try and figure out what it is, but let me show you a little trick. Makes life a lot easier. Nope, you can't just add a no. What if I took, in math people, and took and times this by 15 halves? Wouldn't that give me 15? Okay, I can't use a fraction, but I'm going to put it here just for a second because that will balance the equation, right? It'll be the same on both sides. Good. So then I use my math brain and say, okay, to get rid of this fraction, I need to multiply this whole equation through by 2. So, 2, 15, 6, 12. Done. Otherwise, I'd be sitting there trying to figure out that that one number in front of oxygen was a 15. And that number in front of CO2 is a 12. And I just have to keep trying figuring back and forth. So if you have oxygens that don't match and you've got an oxygen by itself, this is a little trick that you can use, okay, to balance. So what I'd like you to do is I want you to try the rest of these. Okay? That's why you do oxygen last, yes, because oxygen can really mess up an equation. Yes?
So for that one, you just doubled everything since you multiplied everything by 2, right?
Right. It's just like I doubled the recipe. Okay? Okay, so I want you to keep going. We're going to put up 1 through 8 in just a minute, or sorry, 2 through 8. I'm going to give each of you an assignment to put up on the board, a number or 2. And then we'll see the others through 15. So keep going, and you're going to put it up on the board. Okay? So let me get my roll book out so I can give you an assignment. Wrong one. They're both white. Yes, sir.
You're the first one wrong. Dividing all by 2 would make the oxygen on the right side 30, so you have to times oxygen on the left side by 30.
Nope. I have 24 here, and I have 6 here. 6 plus 24 is 30.
Yeah, and then on the other side it's 15. And then
15 times 2 is 30. It's already there. Okay? It's all right. Sometimes you just need another look at it. It's always good to question. Okay. Okay, let's see. Kyle, I'm giving you number 3. Alex, I'm giving you number 2. Jesus, I'm giving you number 4. Let's see. Jaron, I'm giving you number 5. Caleb, number 6. Ashley, number 7. And Kaylee, number 8. Is Aspen back in here? Yep. You're going to be 9 on the next page.
So if it's just 1, we don't write it in.
Right. Don't write in if it's a 1. Tyson, you'll be 10. Cambry's not back in here. Emma's not here today. Richie, you do number 11. Is Luke back in here? No, Luke's not back in here. Brian's not in here. Ben, you're doing 12. And then Kyle, I'm giving you 13. Caleb, I'm giving you 14. And Jesus, I'm giving you 15. Okay, so as you get them done, 1 through 8, let's get them up here on the board. If you need help with yours, let me know. That way, even if you don't get through them all today, the answers will be up on Canvas, and you can practice and then go look and see if you've got the right answers. Okay? Good. So if you need help, pull me in. Get yours done, and let's get them up on the board, and then you can go back if you need to and watch the Canvas and get the answers. Yes.
So I missed a bit. What do you do here? So we got to find out.
Okay, so then you're going to go one sodium, 2 sodium, so I need to put a 2 in front of that.
Okay. Makes sense.
Then 2 iodines, 4 iodines. I need to go back and change that 2 to a 4 now.
Right.
And by doing that, so I'll put a 4 here, then it also makes 4 sodiums, right? Right here, NAs.
Oh.
Okay, that means I need to put a 2 in front of this so that will change to 4. So cross it out, put a 4. Okay, now one lead, right?
Right.
2 sulfurs, 2 sulfurs, 8 oxygens, 8 oxygens.
Right.
Done.
So you don't do anything here?
Nope. Nope. Okay, as soon as you get yours done, get it up on the board because we've got 3 more that we need to get, 4 more. 4 more we need to get up real quickly. And then we can go to the next page and have you guys put those up. So 1 through 8 need to be up. So if you had numbers 1 through 8, put them up. You need help. Okay. This one? This one right here? 4, 12 oxygens. 6 and 6 is 12 oxygens. 12 hydrogens. 12 hydrogens is done. Except this should be lower ratio. Right? So take it down. Sorry. Good question.
Whoops.
So what if we just went down lower than that? Put a 2 here, right? Because we need 2. That would make 6 oxygens. Put a 3 here. 3 and 3 is 6 oxygens. 6 hydrogens. 6 hydrogens. So when I look at them like you had, and I can divide all of them by 2, then I know I went too high. Okay? Okay, we have 2 more that need to get up, 5 and 8. If you're 5 or 8, let's get them up so we can go to the next page and get the next ones up.
Nah, man, 13 it's easy. You only times 2 of them by 2, then you're done.
Okay, so both of them are up. Is there any questions on any of the ones that have been put up?
Did I do number 3 right?
Number 3 is done correctly, yes. Okay, so those are the answers. If you need them, they'll be back on Canvas. 9 through 15, you're up. I seem to have this aversion to giving short people the tall one, right? I'm sorry. May just stretch high.
It's weird writing these.
Yeah, you gave the pretty tall people the...
Lower ones. They're usually trying to... Yeah. You did it. Vanadium.
There's one that's Y.
Yep, yttrium. Yttrium. Sorry, yttrium is YB. Okay, who has 15? Come on, that's an easy one.
It looks hard.
It looks hard, but it's an easy one.
Because the aluminum's already done. Yeah. The oxygen's already
Do your nitrogens, and that'll help you.
Dude, this is so easy. We did this in like 8th grade.
Mm-hmm.
do the anchor.
Yeah.
This is what I found.
Okay, so now do your hydrogens. So you have 3, and 3 is 6. You have 2.
Why?
Because
So
I could.
put a,
I took biology.
so 2 times what is 6?
Yeah, because the biology.
So that's all you need to do. Go.
Dude, he was the greatest.
Okay, so we're going to go through the next part rather quickly because we're going to redo it on Monday with all the demos. So, right here, 3. Okay, good. So we've got all of them, and I checked them as you put them up. You did a great job.
Would it be bad if someone inhaled them on you?
Yes.
How bad?
You want to burn your innards?
Well, what if it was just a little?
If it's a little, it's not a bad deal, but... Okay, so types of reactions. We have chemical reactions. That's a big overall arching. It breaks down into non-redox and redox, and we're going to talk about non-redox and redox a lot more later. But then we break down into double replacement. Double replacement is always non-redox.
Non-redox.
Okay, yep. Decomposition and combination, synthesis and decomposition, can be either redox or non-redox. It just depends on how they're doing it. And then the last two, combustion and single replacement, are always redox. Okay? So they're always redox. So this is just a chart to give you the types of reactions that we'll be working with over the next little while.
The other one's decompensate.
Decomposition's right here. And then we have synthesis combination here, combustion, which is a redox reaction, and then single replacement or substitution. So I think the only one we're still missing is Luke.
That's a lot.
Is that how much we've done already?
No, that's how much we have to go.
I know.
Yeah, Luke was having problems when he, like, with a hot plate and the ice, but in a solid rock thing, he could not, like, someone gave him the wrong information.
Okay, going forward here, I want to just get through the types of reactions if we can. Okay, so we'll talk about acid bases in Chapter 9. We're not going to talk about them today, but that is a type of double displacement or double replacement. So synthesis basically is putting two things and getting something new. So they're separate, now you have a couple. Okay? So synthesis is putting together, decomposition is pulling apart. It doesn't have to pull apart to its elements, though. It can just have one thing falling apart into a couple things that still can be compounds and some elements, or just two compounds. So decomposition, when it falls apart, it can fall apart from a compound to two new compounds. It can fall apart to elements. It can fall apart to elements and a diatomic. It can fall apart like what we did in lab from ammonium hydroxide to water and ammonia. So the ammonia is the gas that came off that when we put our chromatography paper over it was reacting with our metals that were on our chromatography paper and making them appear. Okay? All right, so we also have single replacement. Think of a dance date kind of thing. The girl can be replaced or the guy can be replaced. Either one can be replaced. Okay? But one gets kicked out. Whoops. Double displacement or double replacement is when you have two compounds and they change partners. Okay, we're going to have to go on from there. Just remind me we stopped at double replacement. Okay?
Want your blue things back or no?
No, just keep them because you're going to need them. We're going to be using them a lot. So just keep those little blue papers. You can use scratch paper too if you want to. Okay? Do you want some? Yeah, I will have this up on Canvas. Yep. So those of you that missed that, go up on Canvas. So that is up to you. That will give you a Weber State card, and then you have some things that you can do with that card. Yeah. Yeah, the library, lots of different things. So it's a good thing to have.